Anybody figured out how they're going to parallelize this? Parallelize the drum head yet? What's your best guess? So subgrids. So what? So like 4x4s or something like that. What do you think you're gonna do? Not yet. Mm-hmm.
Well, I'm thinking if I would just use 100 parallel processors, like one for each node, probably work the best.
So takes a lot of space, but so you make smallest possible CPUs. Yeah, we do have the bigger boards. We have the DE2 115s, which have 4 times the logic elements and several times the memory and a whole pile, 480 multipliers or something. I think, Luke, did you try getting that running on Friday?
We got about to run on it.
How hard was that to do?
Hard. The generator generates
All right, so the top level, so there's a, what do they call it, a application generator or interface generator? Something like that. So you take the DE2 115 out of the box and you dig around underneath. There's a disk, and then on the disk is some application stuff, and I'll get that up on the website, but I don't have it up there yet. But you can put it on the machine, and it allows you to choose what peripherals you're going to use on the board, and then after you choose the peripherals, it generates the top level file for you, a top level file template. And that's how you then start the project. Was there any trick in building a project that you found? Just worked as you'd expect. You have to change the device target, I think, in the project, right? Right. No, 27 megahertz. Really? So how do you generate the video signals?
we used the 50 megahertz to generate another
Okay.
And then when it came to sample frequency,
Right. Okay. So it all worked. Okay, good. So who else wants to hazard an opinion? What are you going to do, Yang? For the, don't know yet? What are you going to do for lab 3? How are you going to parallelize it? You only got 2 weeks. You got less than 2 weeks now. This is a hard lab. This is a hard lab. So you really need to be going on this. You need to have started thinking about this. Evan? No CPU. So multi-node state machine, single node state machine.
probably a separate state machine for each node.
Yeah. The one limiting thing about a state machine for each node is, well, first of all, it's really simple to think about, and that's good. And the connections are quite uniform and easy to lay out, but it's hard to keep it busy. Right? It's hard to keep it busy because there's not enough states that are required between audio updates. Unless, oh, how about this? Let's not make it a parallel don't make it an 18-bit processor. Make it a serial 1-bit processor. And then you put lots of them on the. So if you made all the arithmetic serial, so all the registers are 1 bit wide. So everything's serial arithmetic. Then going to a node one computational node per state machine would make a lot of sense. So all arithmetic is serial. So every add takes 18 cycles because you're doing bit serial arithmetic. Every multiply takes who the heck knows how many cycles. Something like that number squared or something. then you might be then it might be reasonable, a reasonable fit to make each node, each computational node a separate state machine. And I wonder how many you could fit on the board then. Clearly, if you use the big board, the DE2115, then we expect more nodes, more computational nodes for the same amount of effort, because it's just easier. You don't have to think very much if you have 480 multipliers versus 70 multipliers. So, what other ways of doing it? Got any idea? How are you going to parallelize? So you're going to go square grid. So nobody is going to use the linear grid scheme, huh? This update one line and then serially update the next line? Interesting. Okay. Well, we'll see how it all goes. I thought I ought to do that generate example, but in more detail again, because while I wrote out the generate, I really didn't do much of the context around it, and so it was kind of slightly understandable, but not too understandable. So I want to do this again. Any questions about Lab 3, about what you're supposed to be doing, what the calculation is, anything like that? Okay, so the plan is I want to talk a little bit about generate statement. Then I want to start on, I want to introduce Lab 4, because Lab 4 is really hard. And it's going to take a week or two to talk about just the basics of how to get it going. And so I have to introduce it fairly soon so we have enough time to talk about it. And the reason it's hard is not particularly because the calculations are hard. It's because I want you to use the NIOS 2 microcontroller, which has a large overhead, startup overhead. It has a high learning curve. Because for Lab 4, I'm going to want you to interface I'm going to want you to use a NIOS 2 microcontroller as an interface between the human and the parallel engine which executes the Mandelbrot, which computes a Mandelbrot set. And since the NIOS 2 is yet another processor, you have to build the processor, you have to learn yet another compiler, and yet another development system. So there's a week of overhead there for you. So you're going to spend 12 hours learning to use the compiler and the CPU. That's why it's a 3-week lab instead of a 2-week lab. But we need to start on that a little early. And then I want to go back and pick up one subtopic, and that is I want to show you a way to implement a second order filter completely in hardware, in parallel hardware, pipeline parallel hardware, rather than as a serial construct just for variety. But also, has anybody thought about special topics that they'd like to hear about for their final project, or because they're interested in them? Start thinking about that. We'll be up for that in 2 or 3 weeks. The last week of classes, we won't have lecture. The last month of classes, we'll just meet in the lab every morning, or every 3 times a week in the morning, for yet more lab time. All right, let's talk more about generator statements. Generates statements. And first thing I'm going to do is define a module. So what we're going to do here is we're going to define a module which is a D flip-flop, which I think you should all be able to do, but we'll write it out anyway. And then we're going to combine the D flip-flop to make a shift register using a generate statement, which is partly what I wrote out on Friday, but I only put out just the minimum, and so the context was a little weak after I got to thinking about it. So there's two 1-bit inputs, clock and in. And there's a output register. Excuse me. Out. And what we're going to do is absolutely the simplest possible thing, and that is to assign out to in on the clock edge. So that's our D flip-flop. So now we're going to define a module top. So this would be like a very simple template for a top-level module with 2 bits of I/O. So we're at equilibrium here. It turns out the amount of chalk on the erasers is large enough that it doesn't actually erase the board, it puts chalk onto the board. So I've never seen that much chalk on an eraser. But the module top is going to have an input from the outside world clock. Going to have a register 3 down to 0 of count, and we're just going to use count here as kind of an internal test bench. A wire 8 down to 0 of path, and an output out. And we're going to always at the pause edge of clock, we're going to increment count. So this is just generating a slightly slower clock, really, because we're going to assign path 0 to be count 3. So we have sort of a divide by 16 clock here, and we're going to assign out to be path 8. So there's some combinatorial statements. Then we're going to, in this context, write out what we did on Friday, which gives the context for this all to operate, that there's going to be a genvar, the generation variable, n, then we're going to generate the shift register that uses this input and this output. So this is very C-like construction, except that the begin in the for block must be named. All right, so this is it has to have a unique name. We can call it for name, we can call it George, we can call it anything we want, but it has to have a name. Colon and name. Every structure within a generate block, if statements, case statements, and for statements all have to have a name, because it turns out they become part of the module names which are iteratively generated. D-flop, and we're going to give it the name U, and I'm guessing the way that what the compiler does is it concatenates the name you put here with the name you put here and an index number to build a unique name for the module. So dot clock is good. So the clock parameter becomes clock. The in parameter becomes path n, and the out parameter becomes path m plus 1. And then this is the, again, still the noise ratio on this board is ridiculously low. So this is out. And then we're going to end the for loop, end generate, and then end module. So this iterative structure generates a shift register because the input of the nth module comes from n, but the output is going to become the input of the next module on the next pass through the for loop. So it's a compact way of generating a sequence of items, which you may well want to do for Lab 3. I strongly suggest that you look up the syntax for case statements and for other structures, because every alternative in a case statement has an associated symbol along with it which must be unique, so that the modules generated can be given a unique name. Because remember, this for loop is actually generating copies of hardware. It is actually generating Verilog code to make you, in this case, 8 copies of the hardware. And you can, the Evans and Sutherland description is pretty good. So if then else case, most of the C-like conditionals work, but you really should look up the syntax if you intend to use it. for making a nice two-dimensional array of processors, this should make wiring them much easier. Any questions on that? Okay, so let's talk about Mandelbrot sets. How many people have a visual of what a Mandelbrot set is? Can you think? Do you have? You got an open laptop. You can find out what a Mandelbrot set looks like. Where are all those iPads when you need them? It's too small. The Mandelbrot set has been called by, on occasion, the most complicated object in math, and is an example of a fractal. Which in this case is a region of finite area with an infinite perimeter. Does that bother you? That something should have finite area but an infinite perimeter? So it's an easy example, right? And which would be to build a triangle, and then on each triangle you erect another triangle, you raise this line, and then on each of those triangles you erect a triangle, and you erase these lines. And it's pretty clear that because you're taking 1/3 of a line and replacing it with 2 lines, that the sum of the lines in each case must be greater than the one before. So if you iterate this to infinity, it never crosses itself, but the length goes to infinity. And yet there's a finite area. It must fit inside of a square about this big. Same is true of the Mandelbrot set. Mandelbrot set is an iteratively constructed structure. It has finite area. In fact, the area is less than 6 in some units or another. And it has an infinite number of interesting properties, but some of those you'll define by looking at them. But you should real soon look this up. It's named after a guy, what's his name? Benoit Mandelbrot, who was an IBM researcher in the 1980s or so, who discovered this. And the basic set is to take the complex numbers in some region we'll talk about in a minute and perform the following iteration. You choose a C. You choose a C, so Z0 is equal to C. And then you iterate this until it either diverges or not. And the region of Z that we're going to consider is 1I minus 2. So it exists in the complex plane. This structure exists in the complex plane. And these are therefore complex multiplies and adds that are required to calculate it. So you're going to be doing complex arithmetic to get this to work. Again, it can be fixed point or floating point. It matters not. But you will find that rather high precision is necessary under some circumstances. And I'll tell you what those circumstances are in a few minutes. So, if z goes to infinity, then you are not in Mandelbrot set. You can show that if the absolute value, if the magnitude of z gets greater than or equal to 2, the system will diverge eventually. So if you run this calculation for a while, your choice of how long, and the value does not get bigger than 2, the magnitude does not get bigger than 2, then you say it is in this Mandelbrot set. If it does get bigger than or equal to 2, you say it is not in the Mandelbrot set. And I would like you to do at least a binary coloration where in the set, not in the set, is some color in the Mandelbrot set is black. You can get fancier. For instance, you could say that the number of iterations it takes to diverge determines the color, or the log of the number of iterations determines the color, which it turns out is a better number than just the number itself, log of the number. But in any case, I'm going to want you to draw at least a binary image of black or some color at 640 by 480 resolution or higher, and to detect if divergence occurs, in other words, if the magnitude gets greater than 2. Clearly, for efficiency, well, you have to choose some cutoff, because if you happen to be at a point near the edge of the Mandelbrot set, then divergence may take a very long time. In fact, it can become an infinite number of iterations required to diverge. Clearly, you're not going to calculate for an infinite time. And still graduate, that is. So we're going to choose some arbitrary cutoff. Let's say n equals 1,000. So if we go to 1,000 iterations and the system is not yet diverged, then we'll call it in the Mandelbrot set. On the other hand, some points on the plane may diverge very quickly, 2-3 iterations, if it's far outside the set. Since you're going to be graded partly on how fast you can calculate this whole region, you're going to want to not do 1,000 iterations at every point if it only takes 3 iterations to diverge. You're going to want to move on and calculate another point. So each point on the plane, the point at which you start, is going to become the C. And at that point on the plane, you're going to plot one of 2 colors, black or white, or some maybe a shade of color, determined by whether or not the system diverges or not. And you're going to do that for every point on a plane which is at least 640 by 480. So it's a lot of points. Your job here is going to be to finish the calculation in the minimum time possible. Last year, the dynamic range in times, the times that students finished in, varied from 28 seconds to 0.25 seconds. So a factor of 100. The people that finished in 28 seconds sort of couldn't get anything running in parallel, and so they were using the microcontroller as a serial processor of the points. The people that finished in a quarter of a second figured out not only how to run several iterators, they ran, in fact, 13 iterators, but they figured out a way of dispatching the iterators, in other words, assigning C's to the different iterators in such a way as to minimize the overhead of the dispatch, which it turned out was rate limiting. It took longer to figure out which iterator should compute the next point than it did for the iterator to actually compute it. And so there was an interesting trade-off between handing out big chunks of points to an iterator and handing them out one at a time. The groups that handed them out one at a time got about a 10 to 1 or 13 to 1 speed up, something like that, so they finished in 1 or 2 seconds. And the people who figured out how to optimally take a chunk and give them to an iterator, a chunk of points in the plane, you can think of various possibilities for how to arrange that. It could be a block, it could be a line, it could be a vertical line, it could be random points. People who figured out a way of optimally dispatching this system got done the fastest. So, unlike Lab 3, in Lab 4, every calculation takes a different amount of time. And what you need to do is load balance. The key word is load balance here. In Lab 3, you're going to find that you know already that every calculation takes exactly the same number of cycles. Every processor finishes at exactly the same time because there are no conditionals. And so load balancing is trivially attained. It just happens. But in Lab 3, you have to worry about communication between points. In Lab 4, there's no communication between points. Every point is completely independent of every other point. Every point calculation is completely independent of every other point. And so you have exactly the opposite situation. You have no communication between iterators, but you have the problem that you want all of the iterators to finish at the same time. Because if one is still going, 10 of them finish in a second, and the last one takes 13 seconds, then your time to finish is 13 seconds. So you have to load balance. You have to assign points in some optimal fashion. So, anybody think of a way to do this off the top of their head? Some points are going to be in the set. Actually, it turns out that, what does it look like? It looks something like this. There's a big black region here, and then a smaller black region here, and then a smaller one here, and a smaller one here. And there are lobes off to the side. So you might guess that if you're inside of a circle of a certain size, you just don't even do the calculation. You just know that you're inside the set. That's a good optimization. But if we were to take a scan line through this whole structure, then some would be very fast because they'd be inside the set, and you could just trivially get them. Some are going to be on the edge, and those are going to be hard. And some are going to be far outside, and those are going to diverge quickly. So maybe taking scan lines And iterating along there and just throwing those out to different processors, one after the other, as you go across, would be a good way to load balance, because sometimes a given processor would get a fast one, sometimes it would get a slow one. And so on average, they'd all come out the same. Maybe. Maybe you should go vertical scan lines. Maybe you should do it randomly, where you pick a random point and compute it. Because then if you biased your random number generator correctly, you'd have an equal probability of being inside or outside the set. So this particular problem is not going to require hundreds of iterators, but it's going to require a good way of balancing the calculation between iterators. Yeah. I believe it is, yes. Well, of course. Any clever iteration, any clever optimization you can think of is fine. You can also do analytical fits to more areas here and just completely eliminate stuff instantaneously from calculation. But then you have to do more pre-processing of a given point before you start to iterate it. And at some point, the analytical fit takes more time than the calculation, because the analytical fit requires getting a radius, which means squaring x and y, getting absolute value. So what I strongly suggest on this particular lab, read up on the Mandelbrot set, read up on the shape, read up on the history, read up about what people have done to calculate it in the past, because there is a huge history on this. There are people who have optimized this for 30 years because they sell postcards of Mandelbrot sets because they're so cool looking. Now, it takes all kinds, you know. Every place you zoom on the boundary, you get a different shape boundary. I'm going to ask you to have a zoom capability in which the NIOS acts as the human interface and allows you to choose the corners of a zoom area. And you'll take this small area, bring it out to the corners of the screen, and recompute a 640 by 480 array around this point. And you can figure out maybe the way you want to define the zoom is center point and upper left corner. Or maybe there's all kinds of upper left, lower right corner. There's all kinds of ways of doing it. But you have to come up with some scheme that appeals to you for how you want to zoom. So you can say, I want to go there and look in more detail right at that boundary right there. And to get some feel for this, you really need to go to, whip up Google, say Mandelbrot set applet, and there'll be 100 of them. And you should start playing with it to see what the system looks like. So when you can't analytically stand to do your DSP homework anymore, or your linear systems homework, go to a Mandelbrot set and play with it for a while. Get a little bit ahead. Get your brain working on this. Start thinking fractal here. Because this is challenging. I would guess that 1 week of the 3 weeks is going to be taken up learning to use the NIOS 2. NIOS 2 is nice because it can use SD RAM for program. You could imagine running a fairly sophisticated algorithm for dispatching points to very stupid iterators, each one of which is connected by a parallel port. NIOS 2 allows you to have as many parallel ports as you desire. You want 50 parallel ports? Not a problem. So it's a configurable microcontroller. You could imagine having an iterator attached to a parallel port. You could imagine the dispatcher running on the NIOS 2, and also the user interface, which is a text user interface, running on the NIOS 2 to a terminal emulator running on the PC. The more bits you keep in the arithmetic, the deeper you can zoom into this structure. It turns out that being able to discriminate inside versus outside requires a fair number of bits, because pretty soon, after a few zooms, you're going to be in a region where the number representation, however you choose it, 18-bit or 25-bit or whatever it is, number resolution, is not high enough to represent any more 1 pixel on the screen. And it doesn't take many zooms to do that. When you're zooming in to 2% of the screen 3 times, you've got now a magnification factor of 50 cubed. So you're going to have to do a trade-off on zoom depth versus number of bits that you carry in the multiply. I think that the lab write-up describes a zoom depth you have to produce. I see furrowed brows. Do you have a question? Okay. I've seen on YouTube, I've seen systems that will do this calculation at video rate, update it 20 times a second. That would be cool. If you could zoom in real time, if you could zoom at animation rate into this structure, that would be cool. It's possible perhaps you could do that on the big boards. I'm not sure. But I don't expect that. What I want is as fast as possible. And it almost assuredly has to be a parallel calculation of several points at once. Because after all, the clock rate on these boards is not that high. However, there's no reason why you can't clock the iterators as fast as possible. You can turn up the clock rate just as high as you can make it go. And as long as you look regularly at the timing evaluator to make sure that you haven't exceeded your luck factor, and as long as that there are still positive slack times in the timing analysis, then the system should operate. I mean, how you set up memory is a different question. I'm guessing you're probably going to want to use SD-RAM for the microcontroller, for the NIOS 2 microcontroller. You probably don't want to put the microcontroller code into M4K blocks, because at least on the small boards, on the original DE2 boards, there is not enough memory on the board to execute a printf. As soon as you put the printf library in the C code, it blows out the 53 kilobyte of RAM you have on chip. So you have to put the program in SD-RAM. You have about 8 megabytes SD-RAM. If you go to the DE2115 board, you've got, what is it, 64 megabytes of SD-RAM? Or 32, I forget which. It's 32 or 64 megabytes of SD-RAM, 4 megabytes, I think, of static RAM, and around half a megabyte of M9K blocks. M9K blocks. You can guess how those probably work. They're twice as big as M4K blocks. The 9 comes in because there's bits for parity control, for error correction. If you decide to use the big boards, keep them separate from the old boards. Put them back where you get them on the bottom shelf. Keep them separate so that we can keep track of them. I don't want them mixed up for now. Maybe later, but not right yet. Any questions? I know we're pipelining lab descriptions right now because we have to get ahead a little bit for Lab 4. And I apologize for that, but there's hardly any way around it. There's just a lot of description necessary to talk about the NIOS too. So keep this in mind as we talk about the NIOS 2, and get out your laptops and do some web whacking on this so that you can find out what these things look at like. Thanks.